All right, so let's start Unit 11 in class. Unit 11 is going to refer to Chapter 14 in your textbook, which is titled Acids and Bases. Starts on page 622. I'm not really sure yet if we are going to just treat this Unit 11 as one chapter, or if I'm going to combine it with two chapters, that being Chapter 15 in your textbook. I'll get to that later, though, once I figure that out. Okay, so really cool chapter, probably my favorite throughout this entire course, and it discusses the acids and bases. It's really neat, very visual lab. So the first thing that we want to do is talk about the definition, or what is an acid base. Let's define that. There's actually three ways that we're going to do that. The first way is with what we call the Arrhenius definition. Arrhenius. The Arrhenius definition says that acids produce hydrogen ions in solution, and that bases produce hydroxide ions in solution. And this is probably the most famous or the most obvious definition for acids and bases. Here's a second way to think about this. This is called the Bronsted-Lowry definition. In the Bronsted-Lowry definition, it says that acids are proton donors. They give protons away. And bases are proton acceptors. So you can see the difference here between the two. The acid definition is essentially the same thing. The difference coming with the base definition. And one of the big reasons why we have these two different definitions is just a little ion known as ammonia, NH3. Based on the Arrhenius definition, ammonia is not a base. But if you've ever worked with ammonia before, it is very basic. It will turn litmus paper very blue. So the Arrhenius definition doesn't work for ammonia. The Bronsted-Lowry definition does, because ammonia, NH3, is super awesome at accepting hydrogen ions or protons. Okay. Oh, one quick note. This thing right here, think about what that is. It is just a proton. H plus is just a proton, because remember, hydrogen in its protein form, in its most abundant form, has no neutrons at all. So if it's H plus, that means that this thing has given away its electron, and hydrogen only has one electron. The only thing remaining is a proton. So H plus is a proton. So you'll hear those two things used interchangeably. So here is a good example of a Bronsted-Lowry equation. HCl, hydrochloric acid, is dissolved, well actually hydrogen chloride gas, is dissolved in water to form chloride ions, Cl minus ions, and H3O plus. In this case, hydrogen is being donated, so the HCl is going to be the acid, and the water is going to be base. You might think, water being basic? Well, sure, it's in the Bronsted-Lowry definition, it is the thing accepting the proton. So it thus then can be defined as being the base. Okay, let's talk about acid in water. When acid is dissolved into water, the acid is the thing that has the proton in front, and the base is going to be water, like I defined on the previous slide. Now, there are two different definitions that we want to get at. There's something called a conjugate acid and a conjugate base. The conjugate acid is formed from accepting a proton. So you can see that the water in this case has accepted a proton to become H3O plus. So all you got to do to figure out what the conjugate base is think of, well, where did that H3O plus come from? Well, it originally was the base. The hydrogen lopped onto it. And so now I have what I call the conjugate acid, and I'll show you why in a second. Okay. The other thing, the thing that has lost the hydrogen, which would be the A right here, that is known as our conjugate base. And here's just a little ball and stick structure diagram, or space filling diagram, to kind of better represent that. So to define conjugate acid and conjugate base, we could say simply that the conjugate base is everything that remains of the acid molecule after the proton leaves. Well, in this case, that's A minus, just some arbitrary number. The conjugate acid is formed when the proton is transferred to the base. We call it a conjugate acid because sometimes, because of equilibrium, unit 10, because sometimes what will happen is this thing will actually lose its hydrogen ion again when it's going back and forth in equilibrium. Well, what do we call things that lose protons? We call them acids. So that's why it gets the name conjugate acid. Okay, here is the third definition of acids and bases. Probably the most obscure definition, but important nonetheless. And you'll actually see on the top of the page, we don't define this in our textbook until 14.11. This is the Lewis acid and base definitions. Lewis acid doesn't look at protons. A Lewis acid simply looks at electrons. And it says that a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. And I have a perfect example down here of aluminum doing this. Aluminum, the 6 plus or the 3 plus on the left side, is going to be known as our Lewis acid because it is going to accept electrons. It is going to accept electrons to then bond with water, and so the water is then called our Lewis base. On the right side, we don't have a conjugate acid or a conjugate base. We have what we might call a complex ion, something that rears its head in chapter 15. Okay, so those are our definitions. And here is kind of a broad table that kind of just encompasses those definitions. Again, we'll see the first two, Arrhenius and Bronsted-Lowry, quite often. Let's talk about acid strength now. This is 14.2. Okay, what makes a strong acid? I mean, what you think about like the horror movies, right? And eating the skin and dissolving the bodies and all that stuff. Crazy. But what actually makes a strong acid? Well, that's actually defined in chemistry. A strong acid is an acid in which the ionization equilibrium lies far to the right. That means that the acid, let's say HCl, almost completely dissociates into hydrogen ions and chloride ions. In fact, it completely, I don't want to say almost, it completely dissociates into hydrogen and chloride ions. And so when we put this stuff into water, there's no HCl left. There's a whole bunch of H on its own, and there's a whole bunch of Cl on its own. That's what makes a strong acid. Strong acids use a weak conjugate base, or they yield a weak conjugate base. So if we think about HCl, I'll do that down here. Hydrochloric acid, really strong stuff, okay? If we put that into water, so this is the gas form, let's put that into a liquid, this is equilibrium. On the opposite side, we have H3O plus, that is aqueous, plus Cl minus, there we go, that is also aqueous. Okay, this guy right here is a really weak conjugate base. Very, very weak base, chloride. Now there is a strong acids list that you're going to need to know for the AP test. I'll go through the names right now and then I'll give you this list on Monday. It's hydrochloric acid, nitric acid, sulfuric acid. We're going to stick with those three right now, and I just want to double check that list later to see if there's anything on there. So the three big ones, hydrochloric acid, nitric acid, and sulfuric acid. Okay, what makes a weak acid? A weak acid is ionization equilibrium lying far to the left. So that means hardly anything dissociates. Generally, the weaker the acid, the stronger its conjugate base. So let's now give two visual examples of this. On the left, we have a strong acid. And you can see that we start with a ton, and draw this molecular diagram in your notes, because this is pretty cool. We have HA, which is our fictitious acid, okay? And it is dissociating. And if you can look at the bubble here, everything has dissociated. Again, as dissociation, what's that mean? Everything breaks apart, right? Or it ionizes, dissociates or ionizes. So everything has broken apart into its constituent ions. So if you take a look at the bar graph, which is kind of neat, we have the same height H and A as we did HA originally. It's a lot of arrows. Sorry about that. So that's what makes a strong acid. On the right side, we can take a look at what a weak acid would be. And if we can take a look at said weak acid, we'll notice that we have the weak acid in the bubble right there. And then on the right side of the equilibrium, And then on the right side of the equilibrium, we see we have almost the same amount of HB. It's probably a little bit less, that bar graph, and very little H and very little B. So we'd actually have a strong conjugate base over on this side. The B minus would be a hugely strong conjugate base, that guy right there. Okay, so there are a couple of ways to describe acid strength. And again, I want you to write this table down. It's an important reference table. It is in your textbook in 14.1, but I think it's important to get down into your notes just to have a quick and easy reference. There's a couple of properties on the left side, like a Ka value. Now, K means the same thing in this chapter as it did in the last chapter. Ka, the A stands for acid. So this is the equilibrium constant for acids. So the Ka value, if it's very large, it means you got a strong acid, because if K is large, it's then going to the right. If it's small, it's going to the left. Got it? Position of the dissociation equilibrium, that's the same thing really as K. If it's far to the right, it's strong. If it's far to the left, it's weak. Equilibrium concentration of hydrogen compared to HA. You see what we've got there. If it's really, really, really small, it's a weak acid. And the strength of a conjugate base compared with that of water. If the conjugate base is much weaker than water, then you have a strong acid, and vice versa. So please, that table into your notes. Okay, and then let's do a little bit about water here. Water itself, really crazy. Water is so cool. It is called an amphoteric substance. An amphoteric substance can behave with either acids or bases. And at 25 degrees Celsius, water actually dissociates a little bit. So if you had an entire lake, you would notice that not all of it would be H2O. You'd have a little bit. I have always said this. If you have Long Lake, okay, in Brilliant, that entire lake, you'd have about a gallon. If you take a gallon jug and fill it up, there'd be about a gallon of hydrogen ions and a gallon of hydroxide ions. And the rest of that lake would be water. Okay? That's kind of a good example. So some of the water actually does dissociate or breaks apart a little bit. So no matter what the solution contains, the product of hydrogen and hydroxide must always equal 1 times 10 to the negative 14th at 25 degrees Celsius. And that fact alone is going to be very important when we're solving some of our acid-base equilibrium problems. All right. So let's talk about neutral solutions and strong acidic and weak acidic and strong basic, weak basic solutions. If the hydrogen ion is equal to the hydroxide ion concentration, we say that we have a neutral solution. So water is neutral because the hydrogen ion would equal the hydroxide ion. If we've got a little bit of acid in there, then we've got more hydrogen ions than we have hydroxide ions. So we have an acidic solution. And if the opposite is true, more hydroxide than hydrogens, then we have a basic solution. And we'll be able to evaluate those numbers and those values using indicators and the pH scale. Okay, that's 14.1 and 14.2. Have a good weekend, everybody.